Module 1, Unit 2, Fleet Transition Using Data Analytics, presented by Andrew Kotz of the National Renewable Energy Laboratory as part of the Virtual Electric Vehicle Deployment for Southeast Asia course. Andrew Kotz is a commercial vehicle research engineer at the National Renewable Energy Lab. He received his PhD in mechanical engineering, focusing on real-world transit bus NOx emissions, vehicle big data, and spatial computing, to help highlight the spatial temporal emissions impacts and identify discrepancies between regulated and real-world emissions. At NREL, Andrew's research efforts have focused on medium and heavy-duty vehicle electrification that explore vocationally specific solutions for enabling battery electric and hydrogen-powered medium and heavy-duty vehicles. In addition, his work has leveraged data analytics to define technical targets and help meet customers' needs. In this presentation, we will go through the background, which explores why do we want to go electric, as well as the technical considerations. We will then transition to how we can leverage data to determine the electrification of heavy-duty vehicles. Various levels of data collection include fuel records, global positioning system data, and global positioning system plus onboard diagnostic CAN data. And at the end, we will discuss some recommendations for a fleet. Why should we go electric? Climate change, air quality, and cost are some of the biggest driving factors behind fleet electrification. Carbon dioxide, which is an emission of internal combustion engines, is the most prevalent greenhouse gas on Earth, making up 82.5% of all greenhouse gas emissions. The societal cost of these emissions is anywhere from $21 per ton to over $900 per ton. And the result of these emissions is longer, hotter summers, more damaging rainstorms, higher tides, and increased flooding as a result of climate change. Air quality is another major factor of internal combustion engine emissions. And another reason to go electric. Criteria pollutants such as NOx, SOx, PM, and VOCs are harmful to human health. Respiratory inflammation can happen in people that are healthy, and increased health issues can happen for those that have asthma. Finally, cost is another major driving factor behind this. Electric vehicles typically have less maintenance and lower fuel costs. Fleet electrification is challenging. There are many different considerations when going electric. Particularly, EVs or electric vehicles are range and charge rate limited. Typical ranges are from 100 to 300 miles, and overnight charging takes anywhere from 4 to 8 hours. And these are for medium and heavy-duty vehicles charging from 30 to 120 kilowatt hours per vehicle. So you might be asking, what information do I need to find? The typical things that we look at when trying to determine electrification potential are the battery size, charge rate, and infrastructure needs. These can be determined from existing vehicle operation, and that will be explored later on in this slide. Various levels of data are able to help answer these questions, and some of this data you might be collecting already. As mentioned previously, various levels of data can be used to determine electrification potential of vehicles. These data include the typically collected mileage and fueling record information, global positioning system or GPS information, which can give you location and speed, GPS plus select CAN information or controller area network information, which can give you location, speed, as well as vehicle diagnostic information, and then GPS plus full CAN data. And full CAN data refers to collecting data points every second on items like fuel rate, engine power, idle time, and emissions. In this section, we will discuss the electrification analysis that can be done using commonly collected mileage and fueling records data. When we start looking at fleet electrification, the first things that we'll ask fleets to give us are the following questions. How many vehicles do you have? The inventory and log of vehicles, including the vehicle ID, owner, vehicle make and engine model, gross vehicle weight rating, miles traveled, annual fuel consumption, and fuel economy. There are additional questions looking at where these vehicles are parked and maintained. This helps us understand both how big the battery size is from the miles traveled and the fuel economy, to what the operation looks like based on the annual fuel use. Additionally, identifying where the vehicles are parked can help us understand where a good place to charge would be. The first use case we'll examine is for an airport ground support equipment fleet. Using their fueling report, along with the thermal efficiency and energy content, we estimate the battery size by multiplying all three together. The thermal efficiency for gasoline we assume to be 27%, with an energy content of 33.4 kilowatt hours per gallon. For a diesel engine and diesel fuel, we assume a 33% thermal efficiency and an energy content of 37.6 kilowatt hours per gallon. Using the equation outlined on the previous slide, along with the mean and max daily fuel used from the fuel record report, we identify a range of battery size that potentially electrify each vehicle type. It should be noted that the idle fuel that's used in each of these vehicles is included in that battery size. However, electric vehicles typically don't use energy at idle. So if one of these battery sizes is bigger than a currently available battery size, it might be worth testing the vehicle before implementing it into your fleet, as the energy use might be less than you expect. In the case that fuel records aren't available, annual hours of operation can be used as an analogous for estimating fuel usage. You have to make some assumptions, but once you make those, you can then use the equation that we developed on slide 9 to estimate the battery sizes. A detail of this process is shown on this slide, along with some of the assumptions that will be needed. For the airline use case, we calculated the annual fuel usage for each baggage tug, belt loader, and pushback tractor, assumed they were the same at each airline, and then multiplied it by the count that each airline had of that vehicle type, which gave us the total annual fuel usage. This can be used to compare your electric vehicle usage to your conventional vehicle usage as an estimate for both fuel savings and cost savings. After calculating the total fuel usage, we then again use the equation shown on slide 9 to estimate the battery size of each baggage tug, belt loader, and pushback tractor. This is the battery size, assuming that that much energy is used in each day. If you wanted to estimate the yearly energy requirement, you would just simply multiply by 365. Next, we'll explore what types of electrification analyses can be done using Global Positioning System Telematics, or GPS telematics. In this example, we explore how to electrify vehicles using GPS speed traces. This study was performed in 2 cities within Mexico, the first one being Mexico City, which is shown on the bottom plot, and the second being León, Mexico, which is on the top right plot. Two bus garages were examined for León, and 1 bus garage was examined for Mexico City. Between September 14th and October 8th, 2017, nearly 14 million data points of GPS data were collected, resulting in 65,000 kilometers of data. GPS was recorded at a 1 Hz or 1 second refresh rate, and 14 buses were looked at in León, whereas 16 buses were looked at in Mexico City. In addition to collecting the GPS speed traces, We also collected the fueling information from each bus garage, as well as the bus information. Here is a high-level overview of the different buses that were used at each bus garage. In Mexico City, there was both diesel and diesel-electric buses, and they were typically 12-meter buses, whereas in León, they typically used 9-meter buses. However, there were no diesel buses in León. This information was used to help calibrate the electrification model that will be discussed on the next slide. Next, we developed a backwards-looking model of the vehicles. We developed both a conventional vehicle model and an electric vehicle model to ensure that our outputs were sound. We started with the knowledge of the vehicle speed, which was collected from the GPS, the mass, which was collected from the vehicle specifications, along with the rolling resistance and drag. Road grade was assumed to be 0, as these cities were relatively flat. The equation for estimating the power of each vehicle is shown in the square box. The plot on the top right is an efficiency map of a conventional diesel engine, whereas the plot on the bottom right is an efficiency map of an electric motor. Both of these maps were used in the development of the model. After developing the model, we then used an equation to calculate backwards from the wheels and determine the rotational speed. We also used an algorithm to mimic the logic of the transmission gear ratios, and then, as I mentioned, the fuel and motor efficiency maps to determine what the output and required engine power was. This physics-based model is ultimately used to estimate the energy consumption of the vehicle on a daily basis. After running the vehicle models across all of the collected data, the resulting fuel economies for both the conventional and electric bus are shown in the top right plot. As you can see, the electric bus has a 3.5 times fuel economy improvement for León, whereas Mexico City experienced a 5 times fuel economy improvement. This is likely a result of the difference in operation between the two cities. León has smaller buses and less transient nature, whereas Mexico City has higher transient nature or kinetic intensity. Kinetic intensity is a metric that describes the characteristic acceleration or power used to accelerate the bus over the aerodynamic velocity, or power used to overcome drag. A vehicle with very high kinetic intensity, such as a bus, has a lot of stopping and going, whereas a vehicle with very low kinetic intensity typically has sustained high speeds, such as a semi-tractor driving on the highway. As you can see, Mexico City by far has a higher kinetic intensity, but León has a decently high kinetic intensity compared to other transit agencies here in the United States. In addition to fuel economy, we also estimate the CO2 reduction from switching from diesel to electric. León had a 45 to 55% CO2 reduction, whereas Mexico City had a near 75% CO2 reduction. In addition to having this CO2 reduction, this will typically improve over time as the grid, which charges the bus, gets clean. We assume that the CO2 production metric for this grid was similar to that of the United States. Next, we use the data to estimate the battery size required for each city. The plot on the top right shows a cumulative distribution of the battery size and percentage of days possible. As you can see, a 300 kilowatt hour battery will satisfy at least 80% of the days for Mexico City and León bus routes. 530 kilowatt hour usable battery is the largest 40-foot battery electric bus available today. Some of the other things to consider, though, are range and range anxiety, as well as degradation. For instance, as the bus ages, it will not be able to hold as much energy, and the bus will not be able to go as far each day. So in the bottom right, we run two scenarios. First, we run the scenario of 85% remaining capacity at year 7 and 85% remaining capacity at year 7 with an additional 20% range buffer. So at the end of the day, when the bus returns to the garage, there will be an additional 20%. Using the max daily distance described by the data, as well as the modeled efficiency of each bus, we estimate that Mexico City will need at least a 535 kilowatt hour battery to complete all of its days at year 7. For the first bus garage in Leon, we estimate that a 514 kilowatt hour battery will be required. And for the last bus garage in Leon, we estimate that a 573 kilowatt hour battery will be required to meet all of the days at year 7. This battery size is larger than the existing battery sizes today. So likely this bus will be phased to less frequent routes as it ages, and as battery technology improves, higher capacity batteries will be needed to complete all of the routes. After developing battery sizes and energy rates for each bus, we then look at the charging. I should note charging is something that we were not able to analyze with the fleet records alone. The main question that we want to answer is, can I charge the bus in time? Transit agencies disproportionately prefer charging their buses at their garage. In order to understand how much time we have at the garage to charge the bus, we use a technique called geofencing, where we use the GPS to understand when the bus goes back into the garage. We then examine the dwell times, or time that the bus is within the garage, to understand how much time we have available to charge. The energy use for each bus is determined from the vehicle model. The average dwell time for each bus for Mexico City was around 12 hours. However, Leon had much shorter dwell times, from 0.7 hours to 1.6 hours. This means that every time that the bus went out of the garage, it completed a trip and came back for Leon, but for Mexico City, the buses did multiple trips before returning to the garage. We examined two different charge rate scenarios. The first scenario is a 30 kilowatt scenario, and the second scenario is a 60 kilowatt charge rate scenario. For the 30 kilowatt charge rate, the buses in Mexico City would take around 6 hours to replenish their charge, whereas the buses in Leon would take around 1.2 hours to replenish their charge. This is concerning because the average dwell time for Leon 2, or the second garage in Leon, was around 0.7 hours, which is less than the 1.2 hours required to charge. So likely they would need to go with the 60 kilowatt charge rate, which was around 0.6 hours to replenish their charge. For Mexico City, there is more than enough time at both charge rates to replenish their charge. However, it would be beneficial to use the 60 kilowatt charge rate if the buses are doing managed charging. The last type of analysis and data collection that we look at is GPS plus full CAN, or controller area network. This explores connecting GPS data to vehicle diagnostic data at 1 Hz. For GPS plus CAN data collection, we collect GPS and CAN data at a 1 Hz rate, or every second. For GPS, we collect time, location, and elevation. For vehicle engine information, we collect engine fuel rate, which can be used to calculate fuel economy, CO2, and SOx emissions. We collect vehicle speed, which calculates daily distance and speed bins. Engine power, which is used to understand the energy production and duty cycle requirements of the vehicle. And then the NOx emission sensors, which help us understand how much emissions we are reducing by converting to electric. Data is typically stored on the vehicle in the data logger and then downloaded and removed. However, some analytics firms use cellular modems to get that data in real time. But for electrification analysis, having data in real time is not necessary. The picture in the top right corner is of a traditional data logger used to understand what is required to make these vehicles electric. The last use case I'll discuss is that of the Port Authority of New York and New Jersey. The Port Authority of New York and New Jersey tasked NREL with trying to identify what the requirements would be to make their yard tractors electric within different terminals in the Port of New York and New Jersey. We analyzed the usage characteristics and the vehicle performance of these vehicles through data logger installation, generating nearly 21,000 miles of data for nearly 7,000 gallons of fuel over 600 vehicle days. Data collection happened between October 9th and November 15th of 2018. Data loggers were installed on 36 vehicles. 14 were at APM terminal, 14 were at GCT New York terminal, and 8 were at Red Hook terminals. These data parameters, which are approximately 50 plus data parameters, were collected at a 1 Hertz or second by second rate. On top of the daily distances determined from the GPS information, the engine CAN network can also provide information on the engine produced energy. This can help understand what the tractive energy requirements or energy required to move a vehicle as if it were electric. The plot on the top left shows a distribution of daily brake energy produced by the engine. On average, we see 120 kilowatt hours of brake energy produced by these yard tractors, with a max distribution of 400 kilowatt hours. I should note that the 200 kilowatt hours is the current battery size of vehicles today. However, the one downside to this method is that energy produced at idle is also included in this number. The distribution on the top right shows a percentage of that energy which goes to idle. The distributions on the bottom left and the bottom right are those same distributions but broken out by terminal. APM terminal uses more energy, up to 450 kilowatt hours, than the GCT New York terminal. This is likely a result of the multiple shifts, showing that it is very important to understand what your duty cycle is before implementing electric vehicles. Much like the process used with the GPS information, we again develop a road load model that's simplified using assumptions based on the vehicle specifications as well as the in-use data. However, the vehicle diagnostic data gives us a better understanding of how to tune our model. In fact, the plot on the bottom right is data collected from vehicle diagnostics of an electric vehicle, and the electric yard tractor motor map, which is shown in the bottom right, is used in the electric vehicle model for this study. After developing the electric vehicle model, the model was then run across all data to generate an emissions profile for both the electric and diesel yard tractors. The first type of emission that was examined was the tailpipe emissions. The CO2 and SOx of the diesel yard tractor were estimated from the fuel use, whereas the NOx emissions were measured from a tailpipe sensor. The electric vehicle did not have any tailpipe emissions. However, it did have production emissions, or emissions from producing the electricity used in the vehicle. This was based on the grid mixture of both New York, where GCT was, and New Jersey, where APM was. Similarly, diesel fuel also has production emissions. The production emissions for diesel fuel are shown in the top left plot, whereas the production emissions for the electric vehicle are shown in the bottom left plot. Combining both the tailpipe and the production emissions, the two right plots show the diesel and electric emissions in whole. Overall, GCT and APM saw a benefit from switching to electric vehicles, and the yearly statistics of fuel consumption eliminated as well as emissions reduction by converting to electric vehicles are shown in the bottom left. The next part of electrification analysis is understanding charging. Hotspot analysis is a key tool in understanding where to locate chargers. As you can see, the darker locations show more frequent stops, whereas the lighter green locations in these plots show less frequent stops. This looked specifically at greater than 60-minute stops to understand where overnight or break charging might occur. As you can see, in the bottom left plot, there's a dark location right next to the coffee shop. So in addition to charging overnight, there may be opportunity to charge while workers are on their break. After developing the electric vehicle model and the hotspot analysis, we can then examine the charge rate and battery size combinations that will allow the vehicle to complete all of its operation without going below 0% state of charge, which we would consider a state of charge violation. The plot on the top right is this analysis performed for GCT New York, whereas the APM terminals analysis is shown on the bottom right. The combination of battery size and charge rate, which allows these vehicles to finish their state of work, is shown in this plot. As the plot gets darker, there are zero of the vehicles are having state of charge violations. However, the lighter the plot gets, the more of the vehicles are having state of charge violations, with that specific combination of charge rate and battery size. It should be noted that the current technology is shown in a red dot on each of these plots. Red Hook Container Terminal, which has been absent in the earlier part of this analysis, was actually analyzed based on one of these vehicle models and GPS speed traces. This had the highest percentage of the vehicles that we examined in this study to be able to be electrified. In fact, all of the studied vehicles were able to be electrified based on current technology. For GCT New York, a majority of the vehicles were able to be electrified. However, APM terminals had the hardest duty cycle, and only 2 of the vehicles were able to be electrified, assuming they could charge when they were stopped for 50 minutes or longer. This is likely a result of their 3-shift operation, and another testament to how duty cycle, or how these vehicles are operated, is important when trying to identify electrification potential. Climate change, air quality, human health, and vehicle costs are some of the key reasons for converting to an electric vehicle. Before purchasing an electric vehicle, it's important to identify the battery size, charge rate, and infrastructure required to meet your needs. Various levels of data can help answer these questions. Daily summaries, which are the most commonly available data, can give you a range estimate as well as battery size estimate just from fuel consumption. However, GPS and CAN data can give you higher fidelity information on whether or not an electric vehicle will work for you. Before purchasing, it is recommended to demonstrate a vehicle from a manufacturer. This will give you better confidence that a vehicle will work for your fleet needs. Thank you for listening, and please feel free to reach out with any questions.